unit that the second unit of advanced higher is electrical phenomena. And just a quick little recap about electrical fields, because that's what we're going on to, electrical force and fields. First thing, what did you notice?
Big spark.
Big sparks, which you've been used to since first year, because the electrons are building up too much charge on that particular top there. It doesn't have enough capacitance for the charge to be contained on there, so they look for a route down the road. The easiest route is going across there, ionising the air as a spark, and then returning to Earth through that wire there. Something else you might have noticed, though, because this was on a couple of rollers. What happened when this started to charge up?
So it got attracted to it?
Yeah, it started trying to get pulled in. And that's because it's experiencing electrostatic force. Any charged objects have electrostatic force of attraction or repulsion. So in this case, it was attractive because this ended up with a bit of positive charge on this side, which we'll come back to later on in the unit. And this has got positive charge attracted to here, and so there's positive and negative, and they attract each other like that. So let's just see that again. It's good to see. So, because the thing's on rollers, that charge pulls the other charged object in towards it. Once they're together, the charge neutralizes and there's less force acting on it. What you can do is set this up with a bit of string, insulated string, and suspend it like a pendulum. So I'm holding that up like that. So what's happening is the charge builds up on here. This has, it's called an induced charge on that side. That's got positive charge pulled across to that side. You get this force of attraction. Once the electrons make that jump across there, it neutralizes the positive charge on here, and you lose the force of attraction, and so it returns back to where it started off from. Then it starts to build up again here, and you get more and more attraction. So we'll just see that again. So it's pulling across there, there's induced charge there, we've got a force of attraction, and then neutralizes, you lose that force of attraction. And after a while it starts to set up a sort of pendulum swing, constantly charging and discharging. Now, if this was further away and this wasn't such a high voltage so that it would actually cause that to discharge, let's just set it up a bit here. What will happen is that the two charges will cause this to pull across, and you can actually measure the charge that's being, relationships that we're looking at in this unit. What do you think actually affects the force of attraction between two charged objects? Say if this one was charged purely positively, this one was charged purely negatively, what will affect how much force there is between the two objects?
Difference between the charges.
Okay, so you've got charge 1 on here, charge 2 on there. That's going to make a difference. What else seems to be making a difference?
The distance between them.
The distance between them. And we're measuring the distance between centres here, rather than the actual distance of separation. So distance between the centres seems to make a difference. The charges that we've got seems to make a difference. Anything else?
Our atmosphere make a difference.
Absolutely, yeah. So the material in between here, if I started sticking things like paper or plastic in between, it's actually going to change the force between the two. So the material that we've got in here is making a difference to the force of attraction between the two objects. We're going to roll all that up as one equation, and it depends purely on the charge here and purely on the charge there, so just multiply that charge times that charge. How about the effect of this radius or distance between them?
Inverse squared.
What makes you think that, Donald?
It's like the same as a point source, sort of.
It's like a point source of...
I don't know. Like stuff.
What, it's same as that, like electricity going out here in all directions and...
Don't see why not.
Absolutely, you're quite correct. Okay. So there's the... What we've got here is an effect. What we can observe is this electrostatic force. Now what's the cause behind that effect? You can't see the cause, you can see the effect, you can feel the, it's a bit like Star Wars, you can feel the force, Luke. So you can feel that force moving between the two, but what's the cause of that effect? What is this imaginary set of lines going off in all directions which you can't see? Again, it sounds more like Star Wars. Electric field. You've got electric field lines coming off in all directions. And because the electric field lines are going out in 3 dimensions from a point source, it exhibits inverse square law in terms of the field. And it's the field which is producing the force, which we'll come back to. Okay, so we can put that all together in one equation, which I'll show you just now. Experiment was originally carried out by an Austrian physicist, Coulomb, who set up a similar experiment, but with, and there wasn't a lot of digital photography around at the time, but what you can see here is there's 2 charged spheres there, and they measured the force of electrical attraction and repulsion using a torsion balance. So running down the middle here, you've got a fiber which, as the thing twisted, they were able to measure the deflection, the twist, as the thing turned around. In fact, if I show you in a sort of enlarged version here, so you'd have one sphere fixed there and another sphere hanging on like that. And then as the 2 pushed apart, that would twist, and the angle of twist on the torsion fiber gave them the force between the 2. The thing had to be carried out in a glass jar because it's so sensitive, the forces are so small, a bit like with the gravitational experiments that you looked at before. So it had to be held in a glass jar. The other thing is that you're going to have leakage into the air with the natural moisture in the air, so some of the charge actually leaked away. A more modern version is this here, where you can set this up. You can buy this from an American company, where you've got 2 charged spheres and the deflections noted again on this torsion balance up there. So you get again this angle indicating the amount of force between the 2 charged objects. That's one way, and this is actually on an American website. This is what a student has set up in a university in America to measure Coulomb's law there. Not such a clear one there. But again, you've got the 2 charged objects, torsion balance to get that small force there. So that's experimentally how it was done and how it still is done, but it's not one that I fancy. I certainly wouldn't recommend it as an advanced higher investigation. If you think your results are frustrating and immeasurable, you want to try this because it's a nightmare. So what does it all show? So if you just put this straight into your notes, Coulomb's law. So you're dealing with 2 isolated, we consider them as being point charges. In practice, spherical conductors will do fine. We've got Q1 and Q2, separated between centers by a radius r. And we're taking this as being in a vacuum or in free space, just in air. So we've got no special material between them. And these are going to be either suspended by insulating threads or somehow suspended in midair, which is always a tricky thing to do. So the force of the mutual force between them is a constant times Q1 times Q2 and then divided by r squared. That's what Coulomb's law actually showed by setting up that experiment there, that as you move the radius between the 2 further and further apart, then you've got an inverse square relationship. The tricky thing is, what was this constant? You've got force in newtons, you've got charge in coulombs. We'll come back to how a coulomb of charge is defined later. It's not defined from this experiment, but there's a constant in here. And the constant is one of the most brilliant constants you're going to come across in the course. It's 1 over 4 pi epsilon naught. And 1 over 4 pi epsilon naught is what's called the permittivity of free space. Now, if you're out parties and things this weekend, just drop into the conversation. Oh, yeah, that'll be the permittivity of free space. And people go, ooh. So epsilon naught so this epsilon, Greek letter epsilon 0, it's permittivity of free space. You can have permittivities for different materials, different dielectrics like plastics and other insulators, but for free space, that refers either to a vacuum or to air. The two are very similar. It's a bit like refractive index of vacuum or air. The two are very similar. So we can use permittivity of free space as being the constant here. The constant itself, epsilon naught, is actually defined from the speed of light. Because the speed of light is related to this, and I'll come back to the relationship with the speed of light later on the unit, and we don't actually need to measure it because it comes from the speed of light. But the actual value itself is, the whole thing is 9 times 10 to the power 9. Now that's the number. What would the units be for that constant? That 1 over 4 pi, the whole thing as a constant is 9 times 10 to the power 9. We just keep the whole thing together. But what would the units be? Have a look at the formula. That we're trying to find the unit for that on its own. So it can't be Coulomb squared per meter squared, because then you'd be multiplying Coulomb squared as well to give you newtons. Chris? Newtons, you're taking meters squared up to the top there, per, close. Absolutely, okay? And that is the most bizarre unit for one of the most bizarre constants that you've come across so far. 1 over 4 pi epsilon naught, 9 times 10 to the power 9 newtons squared coulombs to the minus 2. So that's what you'd be using when you're trying to work this out. Now, just to plug the numbers into that is pretty much a no-brainer. The thing is that you've got to be careful that the units have to be in coulombs. And quite often you're dealing with very small charges, so you may have to convert from nanocoulombs to coulombs. And similarly, the distances could be quite small, but you've got to work in meters. And then you'll get a force in newtons. So let's just try an example of this, and then we'll try something a little bit more complicated, the sort of thing that you're going to get asked in an exam on it. So what would be the attractive force between two smoke particles which were separated by a few millimeters? So the smoke particles have got a charge 2 nanocoulombs and minus 5 nanocoulombs. The smoke particles would obtain that charge under the ionization from a flame, like a match being struck or something like that. And they're going to be separated by just a couple of millimeters. So Q1 be 2 nanocoulombs, Q2 minus 5 nanocoulombs. R would be 0.002 meters. And we'll try to find the force. Just try that yourselves just now, just as a full example. You should get a force of 0.022 newtons mutually between them. That means that if you hold this one steady, that one would be attracted with a force of 0.022 newtons. If you hold that one steady, that would experience a force of 0.022 newtons. It's a mutually attractive force.